calculation will be easier, right? So power unit system actually is your what you call uh, just 1 minute, just 1 minute. So power unit system is for I mean whatever we'll do now from the for the next all these chapters, everything will be done on power unit system. So what is power unit system? Power unit means dimensionless quantities, right? So how to do this? I mean how to do this? And later we'll show you that whatever transformer parameter you have studied, refer to primary, refer to secondary. In power unit system, you will find on either side the value will remain same. For example, you just think, and another thing is that in electrical engineering, that power network, basically it's a three-phase transmission line and a balanced network, right? So what we do, instead of drawing all the three lines for phase A, phase B, phase C, it is difficult to solve because the circuit diagram itself will become very complicated, and that's why we represent the three-phase system by single line equivalent diagram, right? Single that we call single line diagram. And as it is balanced, so phase difference is 120 degree apart. So if you get the quantities of one phase, naturally if you want other, everything will remain same, only angle will be shifted by 120 degree or 240 degree or minus 120 degree, 240 minus 240 degree, like this, the way we want, right? So basically we represent that your all these quantities in dimensionless quantities, and instead of drawing three-phase circuit, we'll make your only single line representation. It makes the your what you call it makes our calculation simpler and easier, right? So for example, if you say single phase representation of a balanced three-phase system, for your synchronous generator you have studied in your electrical machines, suppose these are the three phase voltage are EA, EB, EC. It is balanced system, right? If EA is EA angle 0, then other EB, EC will be, EB will be minus 120 degree and EC will be plus 120 degree or minus 240 degree, right? It is a balanced system. And this load ZL, three impedances, this is a balanced impedance load, and hence there is theoretically there is no current flowing to the neutral, so IN is equal to 0, right? Therefore in this case it is neutral, it is connected, it's a balanced system, so no current is flowing to the neutral. Now whenever we go for a single line diagram, so you go for a single phase representation. Single phase representation means this is your reactance is given, say ZG, generator reactance is given ZG, and this is your ZL. Then only single phase you are doing that, your circuit diagram we are making it, this plus minus, that is A, instantaneous polarity, this is ZG, current flowing through this IA, and this is impedance ZL. So instead of solving all the three phases, we'll solve for single phases, automatically other three will come out, right? So this is the single phase representation of a three phase system. So everything will represent by single line diagram rather than drawing all the three phases. This is a single line diagram, right? Only single phase we are representing. So as if it is a single line diagram, three phase transmission line also later we'll draw by single line diagram, right? So this is your single phase representation. Now whenever you write down this using KVL in this equation, you can write that EA is equal to ZG plus ZL into IA. So that is whatever is written here, EA is equal to ZG plus ZL into IA, right? So this is your figure 5.2. That means this figure, right? This figure, it gives the single phase equivalent of balanced three phase network, right? Of this figure 5.1, this is a single phase representation, right? So now as the system is balanced, the voltage and currents in other phases have the same magnitude but are shifted in phase by 120 degree, right? So these way things are. Now what we will do, that now we represent the transformer, right? So now consider the case where a three-phase transformer forms a part of three-phase system. So three identical single-phase transformers, your what you call, may be connected to form a three-phase transformer. The windings can be connected in four ways: star star, star delta, delta star, or delta delta. The phases of star star and delta delta transformer, there is no phase shift between corresponding quantities on the low and high voltage windings. Whatever you have studied in your transformer, I believe you have studied, or YD11, YD0, all sort of connections you have made it, but here we will not do anything. In reality, actually, for a large power transformer, it is not a three-phase winding together. What they do it, they make three single phase transformer, and they connect it according to the three phase. After that, they connect it together to make it three phase. Because if by chance in one phase there is a fault, and if it is a combined three phase winding together, if it is designed like this, then for repair other thing, you have to carry the all the three phases to the industry, your what you call, to industry to repair that one, right? But if three single phase transformers are connected in your as a three phase, if one phase has something wrong, say insulation problem or something has from fault has occurred, so that particular unit can be removed from this three phase and can be taken, such that your what you call, that your cost of transportation, other things will be less. So in reality, all the power transformer, whatever you see in transformer, three phase transformer, basically three single phase transformers are made it together, right, to make three phase according to the your what you call voltage, high voltage side, low voltage side, accordingly it is designed. So for large transformers, basically three units of single phase are connected as three phase. So here also, here also some three single phase transformers are shown, and accordingly it is connected. This one is connected star star and star grounded. This is primary side, this is secondary side, this is primary side, this is secondary side, this is primary side, and this is secondary side, right? If you look into that, from primary side, this one A to N, this one and this one, all three are connected together and making a neutral, right? This is your grounded, star grounded. Similarly, this side also, if you look, this is taken out, this is taken out, and this is taken out, star grounded, right? And this side, it has been made your this side. If you look into this point A, B, and C, so it is forming a star connection. This side also, secondary side also, it is forming a star connection, but both sides are grounded, right? So this is the schematic representation of this transformer. Now if you this is what is your schematically it is shown, and this is whenever you are solving circuit problem, this starts your three phase transformer. This is the primary side and this is the secondary side. So this way we connect, right? So this is your ABC, and all the currents are flowing through this phase A, B, C, and this is neutral. And this side also, the way it has been marked, accordingly it is drawn. You can draw it in other way also, right? And it is capital N and this is small n, and this side voltage is VAN, VBN, VCN. This is the primary secondary side, and this is the primary side. Now, if it is a balanced thing, so this can be represented by single line, or single line diagram. So say for phase A, this is VAN, current flowing through this is IA, and this is your what you call VAN, secondary side, and current going out. If load is connected, this thing, but schematically it is shown, right? And this is your what you call star star, whatever it is shown here, figure 5.3, this is the star star. So this way single phase we represent for the transformer, right? This is for star star connection, this is star star connection, right? Another thing is, this is your number of turns are there for each phase. Say if it is primary side, it may be NP, NP, NP. If it is secondary side, it may be NS, 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 right? So number of turns will be there, but this way we represent, rather than as a three phase, because it is balanced system. So all these quantities, whatever you will get, only 120-degree phase shift, right? So this is a single. This makes our calculation easier, right? Similarly, if it is a star delta, so star side, this side remains same. A, B, C, and this side neutral is there. So this side star side, this side is okay. I mean same as before, same as this side. This side is okay, right? And this side is delta side. So this is if you look into this A, B, C. So it has been connected to your A terminal is taken out, B terminal is taken out, and C terminal is taken out, right? And accordingly this connection is made as a delta. Look here, this is connected to this is connected to this, and this C, B, and A taken out. So this side is a delta connection, right? And if you make start to delta, see star is remain as it is, same as before, same as before, star, right? And this is the delta. And if you want to make it equivalent one, this is suppose this side your this N2 so secondary turn is N2. If you want to make it as if some equivalent star kind of thing, then this turns should be the stance your what you call the turns will be N2 by root 3, N2 by root 3, and so on, right? So this way if you represent this side is star, that is your your what you call VAN, right? And this is your this side, if it is primary side is N1, the ratio is N1 is to N2 by root 3, and this side is star and this side is delta, right? And this is your AN, the way it has been made, right? So only thing is that one your typographical error is there. This side should be capital A, capital N, and this side should be small n, right? Just it has been it is your just typographical error. This side should be capital A, capital N, this side should be small n, right? And this side is N1, I mean this side is N1, and this side is equivalent star, we have made it. That's why this turns ratio is taken N2 by root 3, right? And this is your how single line diagram, and this side is star grounded, that's why star it is grounded, and this side delta, right? So this way we represent your transformer as a single line diagram, right? So this is actually, it is not per unit system, but before moving to per unit system, that this is how we represent generator, transformer, and after that transmission line, everything should be represented by single line diagram instead of all the considering all the three phases, right? So when we draw single line equivalent, it makes our problem easier. Now the per unit system. Actually, power system quantities such as current, voltage, impedances, and power are often expressed in per unit values. For example, you choose some base voltage is 220 kV specified, say, but the voltage is 210 kV, then in per unit value it will be 210 by 220. For example, it is 210 by 220, so 0.954 per unit, right? If you choose some base, suppose some transmission line voltage is 210 kV, but if it is 220 kV your base, then you can convert it to dimensionless quantity 210 by 220, right? That is 0.954 per unit, say. So major advantage of the per unit is that by properly specifying base quantities, the equivalent circuit of transformer can be simplified, right? When expressed in per unit value, the equivalent impedance of a transformer, whether referred to primary or secondary, is the same. That we will see later, right? Another advantage of the another advantage of the per unit system, your what you call that this comparison of the characteristic of the various electrical apparatus, different types and rating, it is facilitated by expressing the impedance in per unit based on their ratings. When all the quantities are converted in per unit values, the different levels disappear, and power network involving synchronous generator, transformers, and lines reduces to a system of simple impedances, right? For example, in general, per unit quantity is equal to actual quantity by base value of the quantity. So we have to choose some base value. For example, suppose S is the apparent power, say, and SB is the base value. So S apparent power per unit will be S by SB. Now voltage per unit value, V is the actual value, and VB is the base value that you have chosen, right? So that is V by VB, that is per unit case. Similarly, current I per unit will be I is the actual value and IB is the base current. Similarly, ZPU will be Z is the ZPU is equal to Z upon ZB, right? So Z is the actual value and ZB is the base impedance, right? Now how to do this? So all this all SB, VB, IB, BB stands for base are always real number, right? So two independent base values can be arbitrarily selected at one point in a power system. You have to choose two. One is two things. One, you have to choose the base voltage, and another you have to choose your base MVA. These two things you have to choose, right? For example, usually the three-phase base voltage amperes SB or MVA base and the line to base voltage VB or KV base are selected, right? Therefore, whenever you choose, like voltage into current is equal to apparent power, but it is a three-phase. That's why root 3 into IB into KV base is equal to MVA base, right? So IB is the base current and kV base is the your what you call that base voltage. So three phase it is, MVA is three phase. So root 3 into kV base into IB is equal to MVA base. Therefore IB base is equal to MVA base upon root 3 kV base, right? And ZB, your this is the this is your kV base, right, divided by your it is actually root 3 into IB base into ZB base is equal to voltage base, kV base, right? So, because it is three phase, so root 3 IB into ZB is equal to kV base. This B actually is suffix, it is written capital B, this thing, it is kV base, right? So ZB is equal to kV base by root 3 upon IB. This is your impedance, right, base impedance. So if you substitute IB from equation 5.4 and here, if you substitute here, so Z base impedance will be kV base square upon MVA base. This has to be kept in mind, that base impedance will be ZB is equal to kV base square upon MVA base, right? This is important because generally for two quantities we assume for power system, one is base MVA, another is base voltage. So ZB is equal to kV square. For example, suppose base voltage, I'm just giving an example, say base voltage is your for example, say here, suppose you have taken say kV base, suppose kV base is equal to say 220, you have assumed, right? That is 220 kV base, right? And suppose MVA base, you have taken say 100, therefore ZB is equal to kV base square, that is 220 square divided by 100 ohm. That is actually 484 ohm. This is the base value, right? So that's why it is kV square base upon MVA base. Now note that phase and line quantities expressed in per unit values are the same, right? Because it is dimensionless quantity and the circuit laws are valid. For example, S per unit is equal to Vp per unit. Actually, what happened? You have everything. You have, I think, first year only up to first semester. Just hold on. Let's move. In your first year, when you came, first semester or second semester, from the middle of second semester, the lockdown started. So in that case, whatever you have studied regarding the power, right? So whatever we do in electrical engineering, because I have not taught you power system. For example, suppose whenever we write the power equation, generally we follow P minus JQ is equal to V conjugate I. Or if you take conjugate on both sides, P plus JQ, it will be VI conjugate, right? Now, why this conjugate comes? Just to capture the power factor angle. For example, suppose if it is given V is equal to say 100, I'm just making it say 100 angle 15 degree volt, right? Suppose suppose it is the voltage across a branch and current through this branch, say for example 5 angle minus 150 degree, sorry, minus 15 degree ampere, right? Therefore, if you just hold on, if you draw the phasor diagram, suppose this is your reference line. This is your reference line. If you draw the phasor diagram, so voltage should be, here it is 100 volt and this angle is 15 degree because it is plus 15 degree, and with respect to reference it is 15 degree. Similarly, it is minus 15 degree. So this side also current, it is 5 ampere and this side will be 15 degree, right? Therefore, the angle between the voltage, this voltage and current, the angle between the voltage and current, that phi actually will be 30 degree, right? Then what will be the power? Power should be is equal to VI cos phi, right? Because that's why if you, for example, if you do not consider that your conjugate, you cannot capture the power factor angle. Therefore, here V is equal to 100 angle 15 degree. Therefore, V conjugate is 100 angle minus 15 degree, right? Therefore, if you follow this convention, this is a convention. If you follow this convention, therefore P, either of these, this one also you can do, doesn't matter, but we follow this, P minus JQ is equal to, it is 100 angle minus 15 degree into I is your 5 angle minus 15 degree. So it is 5 angle minus 15 degree is equal to 500 angle minus 30 degree, right? Therefore, if you separate real and imaginary part, it is 500 cos 30 degree, that is VI cos pi, 100 into 5 cos 30, and Q will be is equal to 500 sine 30 degree, because it is your 500 angle minus 30. So 5 cos 30 minus j 500, 500 cos 30 minus j 500 sine 30. So separate real imaginary part. So P will be this much and Q will be this much. That's why we use conjugate, right? Either P minus JQ or P plus JQ is equal to this. If you define this is as a, or what you call, this is as S is equal to P plus JQ is equal to VI conjugate. If you define this, or if you make it S conjugate is equal to V conjugate I, that is what is this one. So that's why here this SPU, when we make that VPU IPU means is PPPU plus J your Q PQ, right? But this thing, that is your S per unit complex power is equal to PPPU plus JQ per unit, right? And VPU is the per unit voltage and IPU is the complex conjugate of per unit current, right? So this way we define that this is the apparent power. And also when you take in the terms of VPU, that is per unit voltage, is equal to Z per unit into I per unit, right? Now when you come to the your what you call three phase load, that S load is equal to, it is V phase into IL conjugate, that is your, this is for V phase into IL conjugate, that is your what you call single phase, and you are multiplying it by 3, right? Because it is three phase. Therefore S load three phase is equal to three phase complex load power, and V phase is the phase voltage. So V phase into IL conjugate for single phase, and if you multiply by 3 it will be total, right? Therefore IL conjugate is the complex conjugate of per phase load current IL. This is star means conjugate. Now three phase load current can be also given as that your the phase load current can be given as IL is equal to V phase upon ZL, right? Because V phase is equal to ZL into IL, where ZL is the load impedance as per this. Therefore, you substitute this IL from this equation 10 in equation 9. If you substitute, then you will get S load three phase is equal to 3 into V phase upon ZL conjugate, right? That means this V phase conjugate into V phase, that is 3 into V phase magnitude square divided by your ZL conjugate, right? Therefore, ZL is equal to 3 phase magnitude square divided 3 into V phase magnitude square divided by S conjugate load 3 phase, right? So basically it's a complex quantity because denominator is a complex quantity and numerator is a real quantity, but overall it is a complex quantity, so it will have R plus RL plus JXL form, right? So also the load impedance in per unit can be given as ZL upon ZB, right? So ZL is this much and ZB is equal to your kV square upon MV, kV base square upon MVA. So ZL is this much, you substitute ZL is equal to this much, and ZB should be equal to kV base square upon MVA base square. You put it, then you will get, this is your expression for ZPU, right? And line to line voltage magnitude is equal to root 3 times V phase voltage, right? So if you square it both sides, so 3 V phase square is equal to V line to line magnitude square. So you can substitute V line to line square here, then you will get ZP is equal to this much upon KVB square into this much, right? Or you will get it, this simply will get it, that this is VL, V line to line square by KVB square. This will become per unit, that's why VPU square, and this is also your S load 3 phase divided by MVA base, if make it, this will be S load per unit. So ZPU will be VPU square upon S load per unit conjugate, right? So this way you can easily, your what you call, we easily transform this. It is an open book exam, so these formulas will be there in front of you, but you have to practice little bit, right? Otherwise even it is open book, you will write online exam, but I have seen, my experience is showing even online also. Just hold on, if anybody wants to join, or no, just hold on. Right. So my question is that you have to practice little bit, right? Directly, if you go and say that I'll go to directly this formula and try to do it, you may not get that. At least my experience shows it is not like that, right? Anyway, so this is actually how to make it per unit thing. I mean, this transformation. Now, another thing is that this formula, that ZPU new, ZPU old, and into your whatever formula is given, and this one actually, actually for what happened, this one, just hold on, that thing is given, for example, for some quantities, if any quantities are there, right? Suppose something is given, so this is your what you call, suppose some case ZB is given zero point 0.1 per unit, right? For example, right? Then say this is base impedance is given, and this is given, this per unit values are given. Say if it is given on 100 MVA base, right? And say 132 kV base, right? These two, I mean, MVA base is 100, and based on this value, it is given. Now, if somebody asks you, find out this ZB in per unit, suppose in the your what you call, using your what you call, say 10 MVA base, say 10 MVA base, it is given, and say you find out 66 kV base, right? So if you do so, these are the old base and these are the new base, right? So what you have to do is, first you have to find out what is the actual value. So that means first you have to find out, this is your per unit, this is your per unit values, not base, per unit value, right? So you have to find out what is the value of Z, right? So Z ohmic value, first you find out, this is per unit value into base impedance, it is given, so kV square, so 132 square divided by your 100, this much of ohm, this is the ohmic value you got, right? Now if you are if you are asked that you find out the what is the new value, new per unit value using this base, so in this case your base impedance is equal to 66 square divided by 10 ohm, right? So whatever you get, divide this by your what you call that 66 square into 10. That means this one should be, again, if you want to find out that per unit value in the new base, then it will be 0.1 into 132 square divided by 100 and divide by this, so it will be 10 divided by 66 square, right? So that will be your new per unit values with this new base, right? So basically what happened, this is your old, this per unit value is the old, right, into this is your old base, that is kV base square, this is old, then this is your MVA base, this is also old, right, into this kV base, this is actually square, right? Sorry, this is MVA base, this MVA base, this is your new, and this kV base, it is also new, and this is square. So what you have to do is that whatever formula is given, that first you find out actually some new values, is the per unit values as given with some base, convert it to ohmic values, and if new values are there, then you convert it to that one. So directly it is written, but when you solve numericals, at that time you will find this formula is nothing. This is a simple one, right? A very simple one. So, so then per unit representation of transformer. Now, whatever transformer you have studied, that is okay. Suppose how we represent the your per unit representation. Now, question is, suppose this side turn is if it N1, this is N2, then N1 is to N2, right? That means whenever we are making it, the transformer, whenever we are making it that basically 1 is to a ratio, actually this side is N1 turn, say this side is N2 turn. So basically it is 1 is to N2 by N1, right? And that is, this N2 by N1 is actually A, right? So 1 is to A, we are making it. And that's why it is 1 is to A. And this side, primary side voltage VP, current is IP, impedance is ZP. And as ZP is taken out from this winding, as if it is an ideal transformer, so voltage across this is EP, and voltage across secondary side is ES, and this is terminal voltage VS, and this is the current IS, and this is the secondary side impedance ZS, right? So now whenever you suppose that this primary side voltage, say PB base, right? This is actually PB VP base, VPB, that is primary side voltage base, and VSB, that is equal to your 1 upon A. In general, you know that your this side in general, when you make Vp B upon VSB, that is your secondary side, primary side base voltage and secondary side base voltage, the ratio should remain same. It is 1:A means that is your, I told you, that is a, basically it is your N1 upon N2. So that is nothing but 1 upon A. So V primary side base by V secondary side base is equal to 1 upon A. Similarly, as the volt ampere base is common for both sides, we can write I primary base by I secondary base is equal to A, right? Because in general, suppose primary side is current is turn is N1 and this is IP. So N1 into IP is equal to your N2 into IS. But we are taking the base ratio will remain same. It cannot change, right? You cannot change that. So I primary base upon I secondary base is equal to A. Right. Now Z primary base, primary side base is equal to V primary base upon I primary base. Right. The way you draw simple your what you call DC circuit or AC circuit. Right. Only thing is that everything we are representing by per unit. So Z secondary base will be V secondary base upon I secondary, sorry, VS base by I secondary base. Right. So now if you go back to this this secondary side circuit, VS is equal to that VS is equal to ES minus ZS IS. This is VS is equal to ES minus ZS IS, right? And EP is equal to VP minus, now if you look at this voltage, EP is equal to VP minus ZP into IP, right? And another thing is that when you take the ratio of EP and ES, that is 1:A is given, so it is ES is equal to A into EP. All these things you have studied in your transformer, your course in the, I think in the, it was electrical machine was in 4th semester. Right. So ES is equal to A into EP. Now what you do, this ES is equal to A into EP, you substitute here. If you do so, VS is equal to A into EP minus ZS IS. Right. And now substitute EP from equation 22, that means from 22, right, and into this equation 4. So this EP again you substitute here, so you will get VS is equal to A in bracket VP minus ZP IP minus ZS IS, right? So this equation, now this equation can be converted into per unit form, right? So this is secondary side voltage VS. So now VS can be written as VS per unit into V secondary side base. So this VS actually we are writing VS per unit into V secondary side base is equal to A into bracket VP, also we write V primary per unit voltage into V primary base. So we are writing VP per unit into V primary base. Similarly, this ZP IP. So similarly, we are writing ZP per unit into ZP base into IP, and in the case of IP, we are writing IP per unit into IP base, right? Similarly, minus ZSIS. So ZS also we are writing ZS per unit into ZSIB and IS per unit into ISIB. Only thing is that original unit here, from here, we are making everything in terms of base and per unit, right? Nothing, just substituting those values. Right? Now divide equation both side by VSB and use, if you divide both side by VSB, so this will be VS per unit, right? If you divide this one and just your what to call, use all the relationship equation 17, 18, 19 and 20, right? So actually this is equation 25. There is a typographical error. This should be equation 26, not 28. This is 27 is okay. This equation should be 26, not 5.28 it is given. So it should be 26. This correction you should make. This equation should be your 26, right? Whatever 5.28 is given, it is actually 5.26, right? And it is 5.28 is given. It is typographical error. It should be 5.26, right? So, sorry. So everything you put it, and then you will get that VS per unit is equal to VP per unit minus IP per unit, ZP per unit minus IS per unit, ZS per unit, right? Now we know that IP upon IS is equal to IP base upon secondary base is equal to A, right? Therefore, IP upon IPB is equal to IS upon ISB. So is equal to, these are per unit quantity. So IP primary side per unit quantity is equal to IS secondary per unit quantity is equal to IPU. So in terms of per unit, that current in the primary side or secondary side both are same, right? Therefore, this relationship you put it here, you put in equation 27, right? You put it in equation 27. If you do so, then you will find secondary side per unit voltage is equal to primary side per unit voltage minus I per unit into Z per unit. This is that your per unit equivalent representation of a transformer, right? So this side is your primary side, this is secondary side, and this is your Z per unit. So irrespective of the refer to anything, whether primary side or secondary side, this is actually per unit equivalent circuit of single phase transformer. This way you represent in our power system studies, right? And rest, ZPU can be determined from equivalent impedance on primary or secondary side of a transformer. On the primary side, the way you have transformed your in your electrical machines, you have studied that Z1 that refer to the primary side, ZP will be primary side impedance plus ZS upon A square, right? But if you divide both sides by Z primary base, then ZP upon Z primary base plus ZS upon ZP your B pi base A square, right? Both side you divide by ZPB. If you do so, this is Z1 per unit, this is ZP per unit, and this is A square ZPB is nothing but your ZS secondary base. So basically Z1 per unit is equal to ZP per unit plus ZS per unit is equal to ZPU. This is referred to primary. Similarly, if you do the secondary side, you will find Z per unit will be equal to ZSPU plus ZPU is equal to ZP primary per unit is equal to ZPU. So whether it is referred to primary or referred to secondary, that transformer impedance, per unit impedance will remain same. This is actually the major advantage of per unit system. So generally, my experience shows that whenever I have given numerical, even in the online mode, online, whatever it is, whenever I have given numericals from the per unit side, I found that 90% students are unable to do it, right? And 10% have done it correctly. This is the thing. So little bit you will practice. Several problems are there. Look, I understand one thing, that online mode, it is really really it is difficult for the this thing, because I understand that maybe some of you may be in the hostel or might have returned to home. Most of you are home also, I assume. I understand you have many courses and online mode. I understand you are missing the campus life. I understand you are missing the discussion about academic discussion, right, with your friends in the hostel. Many things are many things are there. I understand everything, right? And considering all these things, we understand. And teaching on the your blackboard and other thing, that's a different thing. And online mode, it's another thing, right? But only thing is that whatever I do for doing for online mode, this I do not refer so many books, only one book for the power system, right? Similarly for design course also, whatever I taught last year or previous or the previous one, and now this year, there also I am sending all my handwritten notes, and they are doing it. For first year student also, whatever I am doing, I am sending my notes if it helps them. Although I am not teaching first year, but I have the notes. I am trying to send every note to them. And your case also restricted to this book only, not following so many books and not sending so many notes. No, no, no. I have no interest to trouble you also, right? So somehow, whatever notes I have in a regular class also, I used to give not only these courses, other courses also. In regular class also, after teaching every chapter, I used to send notes to the student through email, right? I had a scan copy. I used to, my philosophy is, I believe that this way it helps to improve the performance. At least my experience also, right? So you thoroughly will study. So many numericals problems are there, right? And that you have to solve it, right? And if you have any difficulty, if you have any time, then go through my NPTEL course, Power System Analysis. All these things are derived and shouted again. I have shouted a lot for explanation. There also you have a see, you can see at least, right, that how things are made, right. If you have a time, little bit you spend time, all these numericals, many things have been explained, and just try to this thing. But online mode, it is really because you are not in front of me, right, and it's really it's a challenging task for teacher as well as for the student also to grab everything. So if you have a time, if you see the NPTEL also, right. Similarly for this thing, for my other students, first year I am taking tutorial classes. There also I have given all my notes to the student if it helps them, and at the same time I told, if you have a time, you can see my first year ET course, which NPTEL, it is there. It is fundamentals of electrical engineering, right. And if it helps, right. But anyway, before closing this, that's one example I'll explain, that a single phase two winding transformer is rated 25 kVA. A transformer rating is 25 kVA, and voltage is 1100 by 440 volt. Frequency is 50 hertz. The equivalent leakage impedance of the transformer referred to the low voltage side is given, that is 0.06 angle 78 degree ohm. Using transformer rating as base value, that is this 25 kV, and this voltage as the base value, you will see that determine the per unit leakage impedance referred to low voltage winding and referred to high voltage winding. Low voltage is 440 volt and high voltage is 1100 volt. Right, now how we will do this? Transformer rating is 25 kVA. You convert it to MVA, divide it by 1000. It will be 0.025 MVA. Primary side voltage is 1100. When you make MVA, you make this is kV, because base impedance is kV square upon MVA. This way you will think, right? So it is 1.1 kV, and VS is 440 volt, that is 0.44 kV. Therefore, MVA base will be this much, and primary side voltage base is then 1.1 kV, and secondary side is 0.44 kV. So base impedance on the 440 volt side of the transformer is, secondary side, it is VSB square by MVA base, so 7.744 ohm. This is actually given your the equivalent leakage impedance of a transformer referred to low voltage side, that means 440 volt side, is given this much, right? Therefore, ZSB is equal to 7.744 ohm. Therefore, per unit leakage impedance referred to the low voltage side will be whatever this low voltage side base impedance is this much, and this is the given. So this will be your per unit value referred to your what to call secondary side, that is low voltage side, 440 side. Now primary side, your referred to the primary winding this thing, so it will be a square into ZS eq, so it will be N1 into N2 whole square into this thing. So it will be 1.1 by trans ratio is basically 1.1 by 0.44, because it is 1.1 kV. We have taken 44, the two voltage ratio, right, V1 upon V2. So that is basically taken your what you call 1.1 upon 0.44 square into this much. So it is actually 0.375 angle 78 degree ohm. That is referred to primary side. That is high voltage side. Referred to high voltage side, right? Now base impedance on the high voltage side is 1 kV, is base voltage 1.1 kV. So therefore base voltage will be your this kV square upon MVA. This is MVA. It is a typographical error, MVA. B not B, MVA base. So it is 48.4 ohm. Now this value you have got, this 0.375 you have got, divide by this 48.4, right, you will get 7.74 in 10 to the minus 3. Angle will remain same, 780 degree per unit. So whether referred to the low voltage side, this value, and whether referred to the high voltage side, this value, it remains same in per unit. Therefore, per unit leakage impedance remains unchanged and has been achieved by specifying this one. This voltage, primary side voltage base by secondary side voltage base, is equal to VP rated upon VS rated is equal to 2.5. This has to be retained, right? So this way, whether it is referred to primary or referred to secondary, per unit values will remain same for a transformer, right? So for this thing, I'm stop sharing now. So today up to this. So again we'll meet on your next week Monday. So thank you very much. But those who are not joining, please ask others to join, right? Although this thing, that thing, otherwise whatever they think, they will do everything in the exam, that will not be that easy one, that that things will be scored online mode exam, this thing, that thing, it will be not. Everyone may get different question, right? I'll set up in such a fashion that 105 students will get 105 different type of questions and different type of data, right? So you have to calculate everyone. I mean, everyone will get a different type of question. 3 or 4 questions will be given in 1.5 hour exam, and every question will have different data, right? I have 4 TAs are there, they will assist me. So data will be different for everyone, right? And things also will be little different this way or that way. Anyway, thank you very much. Again, Monday we'll meet. So thank you. Thank you.
Thank you, sir.
Okay.
Thank you,
Okay.
sir.
Okay. Thank you.